In this video, we discuss learning outcome number 2 for lesson 10.2, which is all about finding that regression equation. First, we're going to describe the requirements for finding the regression equation, and then we'll talk about 3 different methods for finding the b sub 0 and b sub 1 that you see in the equation itself. So let's start with a little bit of a review. Given a collection of paired sample data, the regression line or the line of best fit or the least squares line is just a straight line that best fits the scatter plot of data. Now we're going to talk more about what we mean about best fits the scatter plot of data in a different video. But for right now, just know that the regression line is that line that best fits the scatter plot. So here's an example. We have 23 pairs of data that relate the Nobel laureates per country to the chocolate consumption in that country. If we plot those 23 pairs of data, we get these red dots over here. That's our scatter plot. This line that is shown here is the regression line or line of best fit, the line that best fits that scatter plot. And I believe this scatter plot was created in a program called Minitab. The equation of that line is called the regression equation. Now, in the equation I'm about to put on the screen, y hat represents the Nobel laureate rate predicted by the regression equation when the chocolate consumption is given by x. So it turns out that the Nobel laureate rate predicted by the regression equation is negative 3.37 plus 2.49 times x, where x is chocolate consumption, with the appropriate units for chocolate consumption and the appropriate units for the Nobel rate. Now this y hat is a predicted value of y. Those are y values on the actual line. They're not the exact y values. The exact y values are the y values that go with a particular x value. There's an x value here and it goes to a certain y value over there. Y hat though, for this particular x value would be this y value, which looks like it's about 12 for x equals about 6.5. So that's what this regression equation does. It gives you a predicted value of y, or the Nobel laureate rate, given a particular amount of chocolate consumption. Now, we should not always come up with the equation of a regression line. Turns out we can always do it if we have a set of ordered pairs. But just because we can do it doesn't mean we should do it. The following requirements ought to be met in order for us to come up with a regression line that is a good approximation of a true population regression line. First, we need to have a random sample of paired quantitative data. Second, visual examination of the scatter plot should show that the points, approximate a straight line pattern. So if you look at the scatter plot and you see something that looks like a parabola, or you see something that looks more like an exponential behavior, there might be a correlation there, but it's not a linear correlation. We should have a linear correlation if we're going to come up with this regression line. And third, if there are any outliers and they're known to be errors, those outliers should be removed because those outliers will have a strong effect on the regression equation. If we have some outliers and they're not known to be errors, that regression equation should be calculated with the outliers and without the outliers. Now, requirements 2 and 3 have little stars by them because these are really our attempts to measure something else. So if you're saying, why do we have requirements 2 and 3? Requirements 2 and 3 are simplified attempts to check these other formal requirements for regression analysis. Here are the formal requirements. For each fixed x value, the corresponding values of y should have a normal distribution. That's difficult to check. Rather than checking that, we're going to check requirements 2 and 3 instead. If requirements 2 and 3 are met, this requirement is approximately met at least. Our second formal requirement is that for fixed values of x, for different fixed values, the distributions of the corresponding y values should all have the same standard deviation. Again, that's very difficult to check, but if requirements 2 and 3 are met, we're going to assume that this requirement is met. Now, this requirement that the corresponding y values all have the same standard deviation is violated if you see that part of the scatter plot shows points that are very close to the regression line, while another part of the scatter plot has points that are very far away from the regression line. So if you see that behavior, this second formal requirement may not be met. And our third formal requirement is that for different fixed values of x, the distributions of the corresponding y values should have means that lie along the same line. Now, checking these things is difficult to check. So that's why we use requirements 2 and 3 instead. If requirements 2 and 3 are met, then we can assume that these other requirements are at least met well enough for us. Okay, so provided that the requirements are met, we actually have 3 different methods for finding the regression line. Now remember, the equation of the regression line is y hat, that is our predicted value of y given a particular x value, is given by b naught plus b sub 1 times x. And b naught and b sub 1 are sample statistics that can be calculated using formulas. So the first way that we can find b naught and b sub 1, or b sub 0 and b sub 1, is to use the following formulas for manual calculations. Now, I know that these look very tedious, and I definitely would not have you use these for large sample sizes, but I want you to be very familiar with the fact that b sub 0 and b sub 1 are sample statistics. They're calculated using our sample data. We use the x values themselves and the y values themselves in order to come up with these 2 constants in this linear equation. The way we come up with them is using formulas like this. Now, in practice, these are relatively easy to compute, even though they look complicated. This just says add up all the x values. This says add up all the y values. This says take the x's and y's, multiply them together, and then add them up. This says take the x values, square them, and then add them together. It's tedious. There's a lot there, but it's all easy. It's just adding, multiplying, and adding, and then once you get these numbers, it's dividing. So even though there's a lot of little calculations that you have to do there, it's good to be familiar where these b sub 1 and b sub 0 come from. It's all based on the data, and that's what I want you to see. So I'd like for you to do at least a few manual calculations using these formulas. Once you understand these formulas and how they work, and you really understand that those b sub 0 and b sub 1 values come from the data themselves, then you can not use these formulas and use other formulas instead, or use technology in order to come up with b sub 0 and b sub 1. All of that is fine, but you should know that those are sample statistics that are actually based on our data, and this is how they're based on our data. Now, these formulas 10.3 and 10.4, are also based on the samples themselves, but they're a little bit more succinct. And now I know that these formulas look simpler, but there's actually a lot more to do here in order to use these formulas. So this says that b sub 1, that's our slope, is equal to the linear correlation coefficient r times this ratio of the sample standard deviations. S sub y is the sample standard deviation for the y values, and S sub x is the sample standard deviation for the x values. This says take the ratio of those 2 sample standard deviations, multiply by the linear correlation coefficient. That's going to be the slope of your regression line. And b sub 0, that's the y-intercept of this. Well, that just comes from taking the mean of everything up here. So we have the mean y value is equal to b sub 0 plus b sub 1 times the mean x value. If you take that and rearrange it to solve for that y-intercept, you get this. So this says that the y-intercept, b sub 0, is the mean y value minus b sub 1, which you can calculate using this formula, times the mean x value. This is more succinct, this is nicer, but again, you can tell that b sub 1 and b sub 0 do depend on our data, because that r value depends on our data, and the sample standard deviations, of course, depend on our data set, and x bar and y bar depend on our data set. It turns out that these are equivalent to these. In practice, these would be harder to calculate by hand, because if you want to find the r value, you've got to compute something that looks kind of like this. To find each of the sample standard deviations, you would have to find the mean y value and the mean x value. You'd have to subtract the means from each of the x and y values. You'd have to square those, add them together, and divide by the sample size -1 in both cases. And then you'd have these sample standard deviations that you could divide and multiply by r. That would be a lot if we didn't have technology. So if I want to use these two formulas, rather than using all of those hand calculations, we're going to use Excel to compute the necessary sample statistics. But I want you to see that if you are doing hand calculations, these are going to be easier hand calculations to do than these, because these actually include a lot of arithmetic that's hidden in that symbol R, which requires a lot of arithmetic. And finding S sub Y and S sub X, that requires a lot of arithmetic as well. So if I'm using formulas 10.3 or 10.4, I'll tend to use Excel to do that computation. Now, lastly, our third method for finding the regression equation is to just use technology. Often technology will just spit out the values of b sub 0 and b sub 1, or sometimes it'll even give you the value of y hat. It'll say y hat is equal to this constant plus this constant times x. That's very nice, very convenient. We're actually going to use Excel's linear regression capabilities. The one thing that I don't like about that is that technology seems to be serving as a black box. You give them all the x values and all the y values, and then sort of magically b sub 0 and b sub 1 appear. I don't want it to be magical like that for you. I want you to understand where b sub 0 and b sub 1 come from. That's why I want you to use these formulas a little bit, at least for small data sets with n equals 4, n equals 5, n equals 6, so that you understand what the technology is doing when it's coming up with b sub 0 and b sub 1 for you. But once you understand what it's doing, it's completely appropriate to use technology in order to come up with that regression equation. So we're going to do all three. I'll do all three in some examples, and we'll see the use of all three in some homework solutions on the elementary statistics homework help playlist. But my goal eventually for you is to just use technology in order to come up with those linear regression equations that look like this. But I want you to know that b sub 0 and b sub 1 depend on the data. And if you say, how do they depend on the data? This is how they depend on the data. Or alternatively, you can say, this is how they depend on the data. Okay, so we know we have these three methods. Provided the requirements are met, we can use these three methods to find our regression equation. Let's actually apply that in an example. Here we're asked to find the equation of the regression line, letting the first variable be the explanatory variable x. The table, which is about to appear on the screen, lists internet users per 100 people and Nobel laureates per 10 million people in 6 different countries. So the internet users are, there are 79.5 users out of every 100 people in one particular country. There are 79.6 internet users per 100 people in a different country, and so on. We've got ordered pairs for 6 different countries. And then we have the number of Nobel laureates in those countries per 10 million people. I know the first time I saw this data, I was like, you can't have 5.5 Nobel laureates, but I guess it's 5.5 per 10 million. So I think that number now makes a little bit more sense. So our goal now is to find the regression equation, if it's appropriate, for these x values paired with these y values. Okay, so the first thing that I would do if I want to determine whether it's appropriate to find a regression equation is to plot my data. I have internet users as my x value and the Nobel rate as my y value. This is an Excel output. This is a scatter plot that I created in Excel. Now, initially Excel had the x values going from 0 to 90 and the y values going from 0 to 12. I changed that a little bit just to make my window look a little bit more square. That's why my x values start at 30 rather than 0. But otherwise, I just had Excel create this scatter plot, as I'll show you how to do in just a moment. Now, before we do anything, we need to check the requirements. In the absence of other information, we're going to assume that we have a simple random sample. Now, if it turns out that we don't actually have a simple random sample, then everything that we do is appropriate for these 6 ordered pairs, but it's not necessarily appropriate for making any predictions of the relationship between the number of Nobel laureates in a country and the number of internet users per 100 in a country if we don't have a simple random sample. So we're going to assume that that's satisfied, but if it's not satisfied, while we can come up with a regression equation that works for these 6 points, that regression equation may not be a very good estimate of some population regression equation if we don't actually have a simple random sample here. Now, in our figure, we see a scatter plot of points. It's very roughly a straight line pattern. I can imagine a line that goes through this. So I would say, okay, that's good enough for us. We can come up with a regression equation, and I don't see any outliers. So the requirements are satisfied. Now, let me show you how to come up with this scatter plot in Excel now. Oops, sorry about that. I'm trying to get my little window to pop back up, but for some reason, there it is. There's like a little toolbar in Zoom, and it's been disappearing lately for some reason. Okay, so here is my data. If I select these values and then I go to Insert, and then I select this little scatter plot icon and select this, then you see that this is my scatter plot. I just changed the range of X values in order to get that square scatter plot that you see in the PowerPoint slides. Since the requirements are met, let's use method number 1 to do our manual calculations. So b sub 1, that is the notation for the slope. It's given by this. B sub 0 is the notation for the y-intercept. That's given by this. And we have our x values and our y values here. Since I only have 6 ordered pairs, this could all be easily done by hand. Now, when I look at the formulas, I see that I need the sum of the x's times y's. So if I'm doing this by hand, I would need to make a column for x times y. I also see a sum of the x's squared. So I need to make a column for each of those x values squared so that I can add them together and come up with a sum of the x's squared. I think that's all I need. So I see these formulas and I know that I'm going to create a table that looks like this. And then in this bottom row, I'm going to add them up. So I'll have the sum of the x's, the sum of the y's, the sum of the x's squared, and the sum of the x times y values. Now I'm not going to do that in this video because it's very tedious, but I just want you to know this x squared here will be 79.5 squared, and this x squared will be 79.6 squared. And this x squared will be 56.8 squared. I'm just going to take each of the x values and I'm going to square them, and I'm going to put them right here. Now in this column, I'm taking the x value and I'm multiplying by the corresponding y value. So I'll do 79.5 times 5.5. That will go there. Then I'll do 79.6 times 9.0. That will go there. 56.8 times 3.3. That will go there. And I'll fill out my entire table in this way. I actually did all of this before I created these slides. So I know that this actually works. It's just a little bit tedious. I'm not going to waste your time with that in this video, but there is another video where I do that in the homework. We go through all 3 methods for a particular homework problem so that you can see how this is done. Now, after I square all of these x values, this is what I get. After I take each of the x values and I multiply by the corresponding y values, these are what I get. And then when I add all the x values in this column, I get this number. When I add all the y values in this column, I get this number. When I add all the x squareds, I get this number. And when I add all the x's times y's, I get this number. Now that I have the sum of the x's, the sum of the y's, the sum of the x's squared, and the sum of the x's times y's, I can substitute all of those into these formulas over here. Notice that we have 1, 2, 3, 4, 5, 6 ordered pairs. So n is equal to 6. I'll just substitute n equals 6 into this formula, these 2 formulas as well. And that's going to get me my b sub 0 and my b sub 1. Now, to confirm all of my answers, I would probably use Excel to do exactly the same calculations. So I come to Excel, I've got my X's and my Y's here. I'll make a column for the X's squared. So I type equals, I select my X value, I use caret, then a 2, that's squaring my X values, and then I just drag and drop. Very simple. For X times Y, I type equals, then I select the X value, then I multiply, that's a little asterisk, then I choose the Y value, just click enter, and then drag and drop from that corner. And then in each of these columns, I need the sum of those. So I'm going to type equals sum, open parentheses, select all the X values, close parentheses, and I get that 399.7, which is exactly what I had on my slides. And if I drag and drop, that's going to give me the sum of the Y's, the sum of the X's squared, and the sum of the X's times Y's. Now, if I want to come up with my formula using Excel, or excuse me, my B sub 1 and B sub 0 using Excel, first I need the count. I need the number of ordered pairs. So here I would type equals count, and it's literally just going to count the number of cells that I highlight, and I'll just pick one of the columns. I pick the X values, and it's counting the number of X values I have, and there are 6. That's exactly what we saw when we just counted our cells. Now, if I want to compute B sub 1 just using my formulas, I can type everything that I need for my numerator right here. Now, I don't actually have that formula in front of me. Let me look at my sheet. Okay. B sub 1 has a numerator that looks like this. It's the sample size, n, times the sum of the x's times y's. That's there, minus the sum of the x's times the sum of the y's. Okay, that's my numerator. And my denominator is the sample size. Oops. That's not what I want. Just want the sample size. Oops, there we go. N times the sum of the x's squared, which is there, minus the sum of the x's squared. So I'll put a caret and then a 2 there. Hit enter. And then B sub 1 should be this numerator divided by this denominator. And I get 0.2028 approximately. Now for B sub 0, the denominator is exactly the same as the B sub 1 denominator. It just has a different numerator. So the numerator for this is given by this formula. I've got my formulas right here on my sheet. This is the sheet that you get to use during your exams. And B sub 0 is the sum of the y's, or the numerator is the sum of the y's times the sum of the x's squared minus the sum of the x's times the sum of the y's. Oh, sorry, that's not right. It's the sum of the x's times the sum of the x's times y's in that numerator. I was looking at the B sub 1 formula. Okay, so that's my numerator for B sub 0. And then I divide by the same denominator from B sub 1. And I get about negative 8.4430 approximately. So that is how I would compute B sub 1 and B sub 0. Of course, you could write all of that down and type it into a calculator, just your handheld calculator, and you would get exactly the same answers for B sub 1 and B sub 0, provided that you're typing it in correctly. Okay, so I deleted those 4 columns and I've just included my summary statistics, or well, my summary, my sums for each of the columns. So this is the sum of the x's, that's the sum of the y's, that's the sum of the x's squared, there's the sum of the x times y's, and we had n equals 6 ordered pairs. So B sub 1 turns out to be equal to this formula. You would never have to memorize that. You'll have that formula with you. And n is equal to 6. Then we multiply by the sum of the x's times y's, which is that 2,301.16. Then you subtract the sum of the x's times the sum of the y's. That's that 399.7 times the 30.4. That's in our numerator. In the denominator, we have the sample size, n, which is 6, times the sum of the x's squared, which is at 27,987.71. And then we subtract the sum of the x's squared. The sum of the x's was 399.7, excuse me. If you do that arithmetic, you type that into your calculator. This is your numerator and that's your denominator. And if you take the quotient of those, you get this, which is exactly the same value that we saw in Excel. B sub 0 is very similar, just has a different numerator. So we have the sum of the y's, which was 30.4, times the sum of the x's squared, which is this 27,987.71. Then we subtract the sum of the x's, which is this 399.7, times the sum of the x's times y's. So that's 2,301.16. You just write that down, do the arithmetic in your calculator, of course, and you get this numerator divided by this denominator. And if you do that arithmetic again using your calculator, you get B sub 0 is approximately negative 8.4430. So that is how we would use the first set of formulas to do manual calculations. Now, I don't recommend using this all the time, but I recommend doing it at least once or twice to make sure that you are familiar with the formulas themselves and where these values B sub 0 and B sub 1 come from. I never want your calculator to serve as a black box. I always want you to understand how B sub 0 and B sub 1 are related to the actual data sets that you started with. This is how B sub 0 and B sub 1 are related to those data sets. Okay. So once we find B sub 0 and B sub 1, we just substitute those into our formula. Y hat is equal to B sub 0 plus B sub 1 times x. And that gives us y hat is equal to negative 8.4430 plus this 0.2028 times x. So that's our first method. Our second method is to use formulas 10.3 and 10.4. Now these formulas are as follows. B sub 1, that's our slope, is the linear correlation coefficient R times the ratio of those sample standard deviations. So we've got the sample standard deviation for y divided by the sample standard deviation for x. And B sub 0 turns out to be the sample mean for the y values minus B sub 1, which hopefully you just calculated, times the mean of the x values. Now, again, I just mentioned what those S sub x and S sub y mean. Those are the sample standard deviations for the x coordinates and y coordinates respectively. Now in practice, if I'm going to use these formulas, I'm going to use technology in order to come up with those two sample standard deviations, the linear correlation coefficient and the two means. But again, if we wanted to, and I don't know why you would want to, but you could, if you wanted to, actually use the formula for R that involves all of those sums of x's and y's and some of the x's times y's and some of, the y squared and the x squared. You could use that and get R. And then you could compute the two sample standard deviations using the formulas that we talked about way back in chapter 3, when we first talked about measures of variation. So we would compute the sample means for the x's and the y's. We would take each x value and each y value, and we would subtract the corresponding mean. We would square those, we would add those together, and we would divide by the sample size minus 1. That would give us two sample standard deviations. That would be a lot. And then of course for x bar and y bar, we would just add all the x's together and divide by the sample size, and add all the y's together and divide by the sample size, and we could get those numbers. But now that we understand how all of those are calculated, it makes sense to use technology to do that calculation for us. That's just arithmetic, but it's important to know what types of arithmetic went into that computation. When we use technology, we never want it to be a black box. We always want to understand what the technology is actually doing. If I use technology, these are the sample standard deviations that I obtain. This is the linear correlation coefficient. This is my x bar, and this is my y bar, excuse me. But those are the same values that I would get if I used those formulas from chapter 3. And I used that formula from 10.1 for R. And if I use the formulas from chapter 3 for x bar and y bar. But let me show you how to compute all of that in Excel. Okay, so my sample standard deviations can be computed in Excel relatively easily by just typing equals here. And then I type ST, for some reason it's giving me an error, ST DEV .s for sample standard deviation. We need the .s as opposed to the .p because there's a different formula for sample standard deviations than there is for population standard deviation. That .s means we're talking about the sample standard deviation formula. Open parentheses and then select the sample. So select all your x values, close parentheses, hit return or enter, and that gives you that sample standard deviation for the x's. Just drag and drop over here to get the sample standard deviation for the y's. For our linear correlation coefficient R, remember that's called the Pearson R sometimes because Carl Pearson is the person who developed it. That's why the function in Excel is called Pearson. So we type equals Pearson, and then it asks for the first array. So that's the array of x values, then type a comma, then select the second array, that's the array of y values, close parentheses, and then we have our linear correlation coefficient. R is approximately 0.799, and then we want the sample means. In Excel, the function for that is average. So we type equals, then average, open parentheses, drag and drop, select all those x values, close parentheses, drag and drop over here so that we're finding the sample mean for the y values. Great. Okay, and now B sub 1 is equal to the linear correlation coefficient R times the ratio of the sample standard deviations. You take the sample standard deviation for y and you divide by the sample standard deviation for x, close parentheses. That value should be the same as the B sub 1 obtained with the other formula, that value. And we see that they're exactly the same. So you might think, oh, that's much nicer. And it is nice, but remember, there's a lot of calculation that went on in the background in order to calculate these 5 numbers. But once we have those 5 numbers, it's really easy to compute B sub 1 and B sub 0. Remember, B sub 1 is the slope. B sub 0 is our y-intercept, and that's given by the mean of the y values minus B sub 1, which we just calculated, times the mean of the x values. And this value should be the same as this value. And we see that they're exactly the same. So you can use the first set of formulas and you get these values, or the second set of formulas and you get these values. I like the second set better personally because we see some of the sample statistics. We see what B sub 0 and B sub 1 are in terms of the linear correlation coefficient, the sample standard deviations, the sample means. This is much less intuitive, but you can see why people used these formulas before. This arithmetic is something that can be easily done by hand. It might be time consuming, but it can easily be done by hand. It's just multiplication and addition. That's why these formulas were used historically. But I like these formulas better because they're more meaningful in terms of the sample statistics that we started with. Okay, so we have all these sample statistics. We substitute them into our formulas, and it turns out we get exactly the same B sub 1 and B sub 0 that we got before. So our y hat is exactly the same as it was before. It's B sub 0, which is negative 8.4430, plus 0.2028, that's our B sub 1, times x. Okay, so that was the second method. The third method is just using technology. Now I'm going to outline how to use Excel to come up with the scatter plot and then come up with the linear regression, equation. But your Excel version may be a little different than mine. Mine is Excel for a Mac. I subscribe to that Microsoft 365, I think it is. So these instructions might be good only for my model of Excel or my particular version of Excel. Your Excel may be a little different, but my understanding is that all of the versions of Excel can do these calculations. You just might have to tweak the instructions a little bit. You might Google it and also Google the version of Excel that you're currently using, or Google the version of Microsoft Office that you're currently using, and then you'll find some instructions online somewhere that will show you how to come up with the regression equation using the technology that you have. But this is how I do it in Excel on my computer. First, I select the 2 columns of ordered pairs, and then I go to Insert. And then there's a little button that has a scatter plot in the picture. I choose that button. And then when I do, I just click it, and all of a sudden there is a scatter plot. in my spreadsheet. Then under chart design, there's an option that reads add chart element. I click on that. There's a little chevron that points down. Then on the drop-down list, I choose trend line, and then there's another drop-down list, and I choose more trend line options. Then once I'm there, there's a format trend line menu, and there's a box that says display equation on the chart. I click that box, and then the regression equation will just show up on the chart next to the graph of the regression line and next to that scatter plot as well. Again, these instructions may differ for different versions of Excel. So this is what I get after doing a little bit of tweaking. Like I made this line red, I put little arrows on the end, I made the equation a little bit bigger. I changed the range of X values from 0 to 90 to 30 to 90. But when I did all of that, I was able to come up with this picture. I also added a title to my graph, but this gave me this regression equation. Actually, I want to show you how I would do that in Excel now, but know that I'm not going to do all the formatting that I did in order to create this image, not in this video anyway. So let's say I want to do all of that. I select my values, go to Insert, click on the little scatter plot, choose Scatter. There's my image. Obviously, I haven't changed the range of X values. I could if I wanted to, but I think I'll leave it alone. Then add chart element, go to trend line, more trend line options. And see the trend line is automatically this dotted line. I wouldn't want it to be a dotted line. But if I go over here to this menu, which is called Format Trend Line, I click Display Equation on Chart. And there's my equation. Now it's very small. So if I want it to be bigger, I have to highlight it and make that font bigger, just so it's obvious and so I can see it. And they're saying y is equal to this. I would probably use y hat is equal to that because it's a predicted value of y for a given x value. And then they give you the slope first, 0.2028 times x, minus that 8.443. That's our y-intercept. Okay, so that's how I got this. And then I did a little formatting. Obviously, I added a title and I changed a few things. Now let's look at the regression equation that was computed using Excel, which was very easy. It was just a few clicks, and the ones that we got using those formulas from method number 1 and method number 2. Method number 1 and method number 2 led to this. Notice that this is exactly the same as this. It's just written in a slightly different order. So they have mx plus b here, or b sub 1 times x plus b naught. And we have b sub 0 plus b sub 1 times x. I'm sorry, I'm using b naught and b sub 0 interchangeably. They're both the same thing. B with the little 0 is sometimes pronounced a b naught. Okay, so that is how we use technology. Obviously, technology is the easiest. I was just creating a scatter plot and adding a trend line and then asking Excel to give me the equation. That was just a few clicks. But I want you to use method number 1 and method number 2 at least a few times so that you understand that b sub 0 and b sub 1 are tied to that data, and they're tied to the data in a very specific way involving the sum of the x values, the sum of the y values, the sum of the x's squared, the sum of the y's squared. Or you can think of it differently in terms of the linear correlation coefficient and in terms of the sample standard deviations and the sample means for each set of values, the sample mean for the y's and the sample means for the x's. So all of these are meaningful and all of them are based on the data. And when we use the data that we have, those 6 ordered pairs that are graphed right here, we get this y hat. And again, remember what y hat is. This is a Nobel rate per internet users. These are the internet users per 100, number of internet users per 100 people in a particular country. And it turns out that that is related to the number of Nobel Prize winners, I think it's per 10 million in a country, by this equation, provided that there's actually a linear correlation between these two variables. We haven't checked that yet. But that is how you would come up with that best fit line that represents the relationship between the Noble rate and the internet users, provided that there actually is a relationship. Now, there's one other thing that you should know before we move on from here. This regression equation. We should only come up with this if the requirements are met. If the requirements aren't met, this line that we came up with, this line right here, it's not meaningful as a regression equation. And if you say, what do you mean by meaningful? Remember, this regression equation that has the coefficient b sub 1 equals this value and b sub 0 equals this value, that's just an estimate of the true regression equation for the population of paired data. So those are the rate of Nobel laureates in a country and the number of internet users per 100 in a country. If we had all the data for all of the countries, and then we were able to come up with a regression equation that included every single data point, that's the true regression equation. This is just an estimate of the regression equation. You give me 6 different data points from that population, and you're randomly selecting those 6 data points from the population of paired data, you're probably going to get slightly different values of b sub 1 and b sub 0. And that's okay, because it's an estimate of the true regression equation. So remember, this is just an estimate, and it's an estimate based on the data. The true regression equation is based on the population of paired data. So it's all the data that is out there, all of the number of internet users per 100 paired with all of the Nobel laureate rates. I believe it's a number of Nobel laureates per 10 million in those countries. And again, that's because it's based, this estimate's based on one particular sample of data. And if we drew a different sample, we'd have a different equation, probably, most likely. Okay, so that's it. That is how you find the regression equation. And that is when you should find a regression equation with those requirements. In the next video, we'll talk about learning outcome number 3, where we discuss a strategy for finding the best predicted value of y given an x value. It turns out that sometimes that's related to the regression equation and sometimes it's not. So I'll see you in the next video to discuss when we should use the regression equation to predict a y value and when we shouldn't.